Here's a circuit I came across. Talking about a few semantics. Notice I1 mesh current, I2 mesh current, super mesh current. The semantic is I1 is placed next to its own individual isolated branch. This happens to be a 1 amp current source. I2 is defined in this 1 ohm branch. The super mesh is defined in this 1 ohm resistor branch. We could have placed the super mesh current here associated with the 4i current controlled voltage source branch, but I chose to put it over here. Makes no difference. In the end analysis, everything ends up being the same. Notice the E voltage, which is the controller for the 2E, the voltage controlled current source. Because E is being used and we need to find what the E voltage is, we had to assign a polarity across the resistor. We had to pre-assign this. Because any voltage is a vector quantity, magnitude with an orientation. We also need I, because for I, this is a current controlled voltage source. I is the controlling current. So we need to fully define what this current is. And we have I being the magnitude, and we have an arrow direction exiting the node. So I as a vector quantity is fully defined. We have a magnitude, I, and an orientation or a direction, which is our arrow. Notice too the current here, which we'll show on the next slide, super mesh minus 2E. As our mesh currents and super mesh currents are always going clockwise. There's no need to show the arrows. There's no need to show any additional polarities across any other resistors, because we're not asking for any voltage across the resistors. We don't need this extra clutter on our diagram. So this is really all we need to ever show. But I will show mesh arrows on the next slide. But as we traverse our super mesh and we come around at the top of our center node here, we see that 2E is actually a branch current exiting the node. So if we wrote a supplemental equation, we would end up writing I sub m minus 2E anyway. And the current for the super mesh and this other branch, these other on the outer perimeter, on the right side perimeter, is super mesh minus 2E. And as we come back here, the 2E re-adds to this, and we end up back with I sub m, because we have I sub m minus 2E plus 2E, puts us back to the I sub m. The same thing would happen if we had identified or defined the super mesh current in this 4I branch. Obviously we could never define the super mesh in this branch here, because we know I1 mesh is also flowing through I. It's not an isolated branch. So I chose to use super mesh definition with this branch here. Continuing here, I'm showing the current arrows, whole flow. We always using whole flow here. I have shown where the start of each arrow identifies where each mesh is identified in its own individual branch. Here we see the super mesh traversing, 2E, reducing the value of super mesh in this right perimeter. And here, of course, we already explained that on the previous slide. The value of mesh current I1, obvious. I1 is equal to 1 amp. You see that right here. The E voltage, we should look at this equation here. We're going to need to write an Ohm's law equation, which is going to be made up of two Ohm's law terms. We see the E equation. We have I2 times 1 ohm resistor. We should actually add, and then we have a negative Ohm's law, a negative I1 times the 1 ohm resistor. We should actually have I2 times I1 plus, and then in parentheses we might have a negative I1 times the 1 ohm resistor, because this is actually a summation. E is actually a summation of two Ohm's law terms. I2, the passive sign convention, positive Ohm's law, I2 times the 1 ohm resistor. I1, entering the negative terminal, passive sign convention, negative Ohm's law. And so it becomes fairly easy to determine the value of E. Next we can find the equation for I. A couple of ways. We can look at this left node and we can sum branch currents in and out of this node. All of the branch currents enter equals exit. I is already defined as a branch current to exit. If we look at the I1 mesh, we might think, oh, well, I1 is entering and then exiting. Say, wait a second here. Even though I is a label, we also have the supermesh current going through the 1 ohm resistor here. So there's no way that I1 is a branch current that identifies and defines a branch current in the 1 ohm resistor entering the node. That's not it. However, I1 is defined in its own branch, so we know I1 is exiting the node. And the same reasoning for the supermesh. We see that the supermesh is entering the node. So we have I sub m is entering, I is exiting, I1 is exiting. If you write enter equal exit and we label that, we can easily see that I is equal to supermesh minus I1. So we wrote the equation for I. The equation for the mesh current I2 is beyond the scope of this presentation. You can write the equations for the mesh loops any way you want. Typically you might traverse, if that's how you want to do it. Again, even if there's no need to label anything else. Do it the way you need to do it. But here's the equation for I2. This allows us to finish, of course, the result for the E voltage, which is positive 0.5 volts. And the same thing happens with the supermesh current. Writing the equation for the supermesh path is beyond the scope of this presentation. How to find the E voltage again. I already showed it using the mesh currents, positive and negative Ohm's law. If I wanted to find the current, the branch current flowing in this, we could look at this right node here, and we see that I1 enters the node, and we see that I2 is a branch current exiting the node. We have two choices to define a current here. We could have the current, somebody can say, well, I want the current to enter the node. Someone else says, well, I want the current to be exiting the node. We know I1 enters and I2 exits. Regardless of what we choose here, E, the E voltage, is always going to be positive 0.5 volts. If we choose a branch current entering this node, we're going to have a positive current going this way, which of course gives us positive Ohm's law, and we're going to end up with plus 5 volts. If we had said our current was going this way, the value, the magnitude of the current is going to be in negative amps. And because this current entering here, passive sign convention, we're going to have negative Ohm's law. So a negative and a negative, we still have positive volts. Doesn't matter. We've already have the pre-assignment of this orientation. So the result's going to be the same. It's possible a circuit could be of an AC nature, where the polarity of this E voltage could reverse to a minus here and a plus here. And that would give us a negative value for the voltage controlled current source, which means the current would actually be flowing into this node. And that's totally reasonable. But here we're working strictly with a DC circuit, so we have a fixed orientation. Here I have defined all the powers for every component, all 8 components, as power absorbed using the passive sign convention. After we find the power for the 2-volt source is 0 watts, we actually see that the supermesh value and the I2 current going through this 2-volt independent voltage source is 0 amps. This 2-volt source could be removed from the circuit. Doesn't affect anything. Kind of a surprise, but I didn't know that until I looked at the power. And looking at the power wattage for all components. Also note too, our right side branch, I sub m minus 2e, this part of the supermesh was never used when we wrote the original equations on the previous frame. The reason is that this branch here only has voltage sources, so the Ohm's law never got used, so we never had to use this current. But now that we're finding power, we need to use I sub m minus 2e, so it's critically important not to use I sub m for the entire supermesh path. This is still equivalent to part of what someone would write as a supplemental equation, which of course later would require substitution. And since we're asking for all the powers absorbed using the passive sign convention, we have them labeled appropriately, -9 watts, positive watts. We see the total power absorbed. All of our positive powers are equal to the total power delivered. 13 watts is equal to 13 watts. Current control voltage source, -9 watts. This is delivering 9 watts to the rest of the system. Our 2E voltage controlled current source is delivering 4 watts to the rest of the system. Our independent current source at positive 2 watts is absorbing 2 watts. And of course, all the resistors are absorbing power. If someone wanted to try to set this up with mesh currents, we'd have to have a mesh current for here. We'd have to have a mesh current for here. And then someone would say, oh, well, we have a supermesh path, and we'd have to write our equation on this supermesh path using a mesh current 3 and a mesh current 4. We'd have a supplemental equation here we'd have to substitute back in. Doing this technique, we eliminated the need of drawing 2 additional mesh currents, and the supplemental equation is kind of already incorporated here. If you've ever worked a 2-loop supermesh with the current source in the middle, and we see the supermesh path, because we can't write Ohm's law for the current source here. If we define the supermesh here going across a 2-loop standard circuit, we would say, oh, this current here, if it was going up, it would have been added to this, a supermesh plus this current, and that would be the current over here. It's another way to do it. We can actually use a real supermesh current, or we can just identify the supermesh path and continue to use standard mesh currents. But then again, in the end, we will need to substitute the value of a current source back into it. So this 3-loop circuit, it's the same thing.